This is Team 3's interim presentation on the analysis and redesign of a manual juicer. A manual juicer is a simple mechanical kitchen appliance used to extract juice from various fruits such as oranges, pomegranate, grapes, and more. The product typically compresses the fruit through a strainer using a linkage lever, a rack and pinion, or a screw mechanism. Based on a model sold on Amazon, we estimate that the annual production volume is 85,000 units. The CAD model we will be using was found on GrabCAD, and it is a linkage mechanism. The model has a total of 12 unique parts, excluding fasteners, using links and shafts to constrain motion and produce force. On the left is a clear picture of our model, while on the right an exploded view can be seen to better see the unique parts, their labels, and interfaces to the assembly.
For our primary customers, we have small businesses such as cafes, bars, juice stands, and restaurants, as they may use juice presses daily. Small businesses may value cheaper mechanical presses as opposed to more costly and complex presses, such as alternative electrical options like larger businesses may prefer. For our secondary customers, we have home users such as families and parents, as well as health-conscious individuals who may use presses frequently and prefer simpler, cheaper mechanical presses. Additionally, travelers and campers are customers as they may not have access to electrical solutions but value fresh juice. The primary function of a juice press is to extract juice. This has subfunctions of press fruit, strain pulp, assure dependability, assure convenience, enhance product, and please senses. Press fruit has subfunctions of apply force and contain fruit. These both have their own subfunctions of convert power, transfer motion, and stabilize press and position fruit. Transfer motion has its subfunctions of constrain rotation and constrain translation. Strain pulp has subfunctions of separate juice and catch pulp. Assure dependability has a subfunction of prevent pinching, while enhanced product has a subfunction of funnel juice.
Here we have assembly sequence A. This sequence prioritizes the ease of handling and placing parts during assembly. It begins with a base, followed by the central shaft, and then moves to the subassembly containing the reamer cone, reamer funnel, and the funnel base. Then we move on to the handle base, the handle shaft, the reamer cap, link A left, link B left, link A right, link B right, and then finally finishing off with the handle link. While this approach focuses on straightforward handling, it becomes less efficient as the assembly progresses due to alignment challenges with upper components, specifically with the reamer cap placement after the handle shaft. Now looking at assembly sequence B, this approach follows a bottom-up method, starting again with the base and finishing again with the handle link, but it changes the order of assembly components to improve alignment and reduce joining difficulties. By assembling certain parts earlier, such as the reamer cap, parts are easier to locate and fasten later in the process. Overall, Sequence B enhances part accessibility and reduces the number of adjustments required during assembly. Finally, this table compares the two sequences using 5 key criteria. As shown, Sequence B outperforms Sequence A in both locating parts and fastening and joining, scoring 3 out of 3 in those two categories compared to 1 and 2 for Sequence A. The other categories, transferring and handling, testing subassemblies, and assembling in parallel, remain consistent between both sequences. In total, Sequence B achieves a score of 12, while Sequence A scores 9, confirming that Sequence B provides a more efficient and effective assembly process overall.
Using our component list from the fishbone diagram and the functions from our FAST diagram, we built a function component matrix linking each part to its purpose. The linkage system is the core mechanism. Its links control rotation and its shafts control translation, converting handle force into the downward press that extracts juice. The base, central shaft, and handle base form the main structure, adding weight and stability. The reamer cone and cap hold the fruit, while the cone and funnel separate and collect pulp. The handle link improves ergonomics and prevents pinching, and the funnel base and base guide the juice down and give the press a stable, balanced feel. Here, you can see the bill of materials for our hand-press juicer. After estimating material, processing, assembly, and tooling costs, the total cost per unit came out to be $79.28. Comparable juicers on the market range from $99.99 to $129.99, so our product sits at about 65% of the retail price of a comparable hand-press juicer. We then determined the quad class of each component, where the cost level was determined by 8% of the total costs, and importance determined by whether or not the task could be completed without the exact part. This helped us identify components to redesign and simplify moving forward.
Now we will discuss product family design. For this, we compared the functives on our FAST diagram with our primary and secondary customer groups to determine what would be different. For this, we determined 2 different functives would be different: collect pulp and assure convenience. This is because the primary group will be using the juicer for longer extended periods of time. To help with this, we wanted them to have the ability to collect more pulp in the reamer funnel without having to empty it every few uses. And we also wanted a redesign of the handle link to a more ergonomic design that promotes extended use. So the 2 main modules this refers to are the reamer funnel and the handle link. The next slide shows the variant changes. The first variant involves the redesign of the handle with an oval shape at the end. This allows for a more comfortable grip for the user. The second variant is a larger reamer funnel to allow for more pulp to be collected, promoting longer use before having to remove the reamer funnel to dispose of the pulp. The main change is a larger diameter cone on top of the funnel. For assembling the different modules, this is both the same for both variants. For the handle link, it has the same attachment as before, where it connects to link B on both sides. For the reamer funnel, it has the same placement in both variations, with the reamer funnel sitting on top of the funnel base. There is no worry over displacement of the reamer funnel when it is installed because the funnel shape on the bottom of the part is the same in both variations, making locating of the part position simplified. Inside, the larger reamer funnel is a ridge to help place the reamer cone. This is slightly larger than the diameter of the reamer cone, making it easy to find the part location for installation. Lastly, the assembly sequence of the original design can be modified so that the variant parts are assembled towards the end, which ultimately will decrease assembly complexity while saving time and money.